Hi everyone, my name is Dan Low. So today I want to keep talking about the MS MIPS 2000 assembly programming and the MIPS 2000 architecture and instructions. So so first, how do we represent instructions? And or another say is that how do we encode instruction so the CPU knows what to do? Okay, so instruction will be sent to CPU. Then CPU will execute the instruction based on the data stored in the instruction. And as the last time we talked about the length of instruction in MIPS 2000 is 4 bytes. So we're gonna take a close look at the 4-byte instruction content. So instructions are encoded in binary. So it's either 0101. There are 32 0 or 1s. It's called machine code. A mixed instruction is encoded as 32-bit instruction words, no exception. All the instructions have the 32-bit length. Okay, and small number of formats encoding operation code, register numbers. So it's regular. Okay, so the register numbers from 0 to 31 from the register number 8 to 15 that represent the T0 to T7, and T stands for temporary storage. And the T8, T9 are registered 24 to 25. So altogether you have 10 temporary registers. Then the S0 to S7 are registered, from the number 16 to 23. So S stands for saved. So sometimes we need, well, basically you can use these 32 registers, at the whatever you like. However, we name it this way. So when you say S0 means this is saved register. So sometimes if you want to use that, you need to save the registers. However, the temporary registers you can use it without any without worrying about whether somebody will use that in later or before. Okay. However, the save register is just convention for writing the assembly programs. But if you follow the convention, your code will be readable, more readable. Although you can use any registers at any way you like. Okay. So here's the MSB R format instructions. I think we have looked at this before. So the LB code is 6 bits, 5 bits for R's, and RT 5 bits, RD 5 bits. The shield amount 5 bits, and the function code 6. Okay. So this R-type example instruction is like add instruction. It's R-type. The R stands for the registers. That means all the operands are from registers. So T1, S1, S2, they are registers. So they provide the operands for the add instruction to operate upon. So if you put the 0, that's all because 0. The function code for the add is 32. 17, 18, 8, that represent the register numbers. Then these combined together, this will be the instruction. This will be the instruction for this add S1, S2, and put the result to the T0. Then sometimes if you see this binary representation is not really convenient, so we normally put the representation into the hexadecimal. So in order for you to convert the binary to hexadecimal, basically you need to group from the right hand side 4 bits at a time, 4 bits a group, all the way to the left. So you got 8 groups. So each group then converted based on this table from the 0 to 15, and then be careful that the number larger than 9, 10, number than 9, the A represent 10. B is for 11, and C is 12, D is 13, E is 14 and F is 15. Okay, so that's the convention. It is lower cases or upper cases that are made. Okay. Now let's take a look at the I format. In the I format, basically, you reserve the constant or address area from the instruction. One instruction. So basically, the instruction, the total is half of the bits are used for constant and address. This 16 out of 32, half. Okay, and then there's a 10 bits, one for 5-bit RS, the source register, and the target register 5 bits, and OP equals 6 bits. Okay, so so basically the constant range will be negative 2 to the 15 to 2 to the 15 minus 1. Okay, then the address, sometimes we just recode the offset, so that will have to add it to the base address in the RS. Okay, so the design principle here is good design demands a good compromise. Different formats complicate decoding, but allow the third loop instruction uniformly. Okay, and I keep the formats as simple as similar as possible. That's the goal. That's design goal. So that's good design demands a good compromise. Okay. So here on the stored program computers, basically invented by Newman. The first computer, the ENIAC and ZIC, invented by two professors in UPenn. Unfortunately, that computer cannot store a program. So after about 1 or 2 years later, von Neumann, proposed the concept of stored program computers. So stored program computer, basically the programs are stored in program memory, non-program memory, program memory of the computer, and that is the processor. So this memory will store the data, the code of the machine code of the program, and anything else. Okay, so the processor will execute the store program. Okay, in this way. So basically, instructions represent in binary just like data. So some, basically this memory also keep the data. Okay, keep the data. So account information, machine code, and then the payroll data. See the data C, and then the book text. Okay, the data, and then source code in C editor. And the instructions and data stored in memory as well. So before you can run a program, the program had to be loaded from the hard drive to memory. Okay, and programs can operate on programs. Okay, so compilers, linkers, they are programs that will work on your programs. And binary compatibility allows compiled programs to work on different computers. So if you have standardized ISA, okay, then binary compatibility allows the compiled program to work on different computers, as long as the different computers knows how to deal with the instruction. Okay, it defined in ISA. So now let's take a look at logical operators. Instructions for bitwise manipulations. So bitwise means the instruction will operate on the operand based on a bit basis. So for example, the shift left. Okay, in C use less than. This operator will shift left 1 bit of the operand. In the MIPS, we use SLL. That stands for shift left logic. Similarly, we can have shift right 1 bit logic is shift right logic SRL. And bitwise AND, like AND or NI. So the NI, anything followed by any instruction name followed by I represent the immediate addressing. That means this instruction will come with a 16-bit immediate value, and this AND will be the the register R type instruction. So all the operands are in registers. And bitwise OR or ORI, and ORI is the immediate addressing version of the OR instruction, and the bitwise NOR. So we have NO NOT, NO NOT, NOR. NOR is NOR, so it stands for the NOT instruction. So that's flip all the bits in an operand. So this is useful for extracting and inserting group of bits in a word. If you want to insert something to a word, you can use OR. Okay, you can insert to it, and you can extract it using AND operation. Okay, so that will get something out. Okay. Shift operations. Now shift operation instruction has this format: the shift bit, OP code, and then RS, RT, RD, each of which contains 5 bits, and the shift among 5 bits, and then a function called shift bits. The shift amount depends on how many positions to shift. So you can shift to the 5, which is 32. Okay. 2 to the 5 minus 1, sorry, 31 bits. Okay, because 5 bit can represent 0 to 31. Okay. And the shift depth logic, the shift depth and shift when you shift the operand to the left, the rightmost will be 0. Okay, the rightmost will feed in the 0. Similarly, if you shift depth by I bits, it's similar. The in math it's equivalent to the multiplies by 2 to the I. If you shift left 1 bit, that means multiply by 2. If you shift left 2 bits, then multiply by 4. If you shift the 3 bits, that's similar to multiply by 8. Okay. Shift right logic, shift right and fill with zeros. So when you shift right an operand, the leftmost will be filled in 0. Okay, so if you shift right 1 bit, that is equivalent to divided by 2. Okay, if you shift right 2 bits, now equivalent to divided by 4. Shift right 3 bits, now equivalent to divided by 8, and so forth. Okay, and this is for the unsigned only, because when you shift right 1 bit, if the most bit is 1, and that's negative, right? Then if you shift right, then negative becomes positive, and that's not good, not okay. And we'll deal with the sign bits later. So first take a look at the AND operations. This is useful to mask bits in a word. So you can select some bits to clear others to 0. So for example, in this case, the ST2 is this. Okay, yes, 0010 0011 here. Okay, and then if T1 is 1111 here, that simply want to mask this out. So only extract these 4 bits out. Okay, that's what becomes 0011. So we're gonna write a program to do this to test it. Okay, so let's go to here. So now this is some test program I wrote. Okay, so let's first set the T2 to this this value. Okay, so we use li. Okay, then T2, and then T2, now we're gonna set it to what will be the value. Okay, this value is 0 0 0 0 0, right? How many zeros? 5 zeros. Okay, so it's 0 0 0 0. Okay, and then this one is 0 0 1 1. That's 3. Sorry, this one's 1 1 0 1. That's 8 plus 4, 12, 12 plus 1, 13. So 13 is D. And then this guy's 1 1 0 0. That's 12. That 12 is C. And then that's 0. Okay. So this is hex. So let's put an H there. Okay. And then let's set a T1 to that number. So Li T1. So the number 0 0 0 0 and then 3. 0 0 0 0 3. 0 0 0 0 3. Okay. And then C00, C00, H. Okay. I think I'm missing the one. 0 0 0 0. Oh, 0. Okay, that's missing a 0 here. 0. Okay. Yeah. And then we're gonna end. T1 and T2, and then put the result to T0. Okay, so save it. Now let's go to the Qt spin and load the file. Okay. Oh, that's a syntax error. Well, it's simply telling that we cannot. We need to use another use some other constants. Okay. So let's go back to check. How do you give a constant? Here I think we have constant somewhere. Okay. Okay, we can put a constant, but we need to tell what value is this. Okay, so let's put the h first. Okay, h, and then try it. Okay. I think we need to find out how to represent a hex constant. Okay, so hold on 1 second again. Okay, so I think we cannot use h. It does not take h to represent hex number, so we put a 0x there. Okay, I represent hex. Save it, and now we can load it again. Okay, now we take it. So as usual, let's set a breakpoint on the JAL main here. Okay, so set a breakpoint, and then run the program, and then yes, we're gonna single step through it. So first we're gonna set the T2, right? T2 to 0DC0. Okay, so T2 is right here. T2 is here. Okay. So that's single step through it. So go to simulator, go to single step, or F10. So now D2 got a DC0. Yeah, that's correct. That's what we want, right? DC0. We can, okay, now we put it, we can change that to the binary data. Okay, and now single step through it again to set the T1 to the 3C00. Okay, that's correct. And then after we and the two numbers together, again we go single step through it. Then we got a T0 is a C00. Okay, C00. Let's go back to check the actual result in the slides. Okay. Okay, there we go. So here the result T0 should be 00000, and it is A4 is a C, so it's C00. So it's correct. The result is correct. So 00C00 is correct. Okay, and yeah, you can right click on this one and change it to binary. Then that'll allow you to check binary. So in the binary, this is 32, right? Not there. T0. That's the binary. Okay. So it's 1 1. It only show the non-zero. Yeah, non-zeros. Okay. So just it only show two up to the leftmost one. Okay. So the best way is you change that to hex. As you can see, that's good about hex representation. Then make it more compact to represent a number. Okay. So that's the end example. Now let's get back. No, let's keep going. The OR operation, same thing. If you can OR the number together, T1, T2, and then put the result to T0. And here the T1 is actually the same number, right? The same number, that's the 3, or not 3, sorry. That's the A4 12 13. So 13 is DC0, right? And then now if we change that, and T1 is same value as we see. So the only thing we change is we change the end to old. Okay, if we do that and then save it, run it again, what happened? What happened is this 1111, this area will change it is 0011 to 1111. So result should be a 3D C0. Okay, so let's check. Okay, no, let's save it and then run it. So I can go file, reinitialize and load the file. Open and then set a breakpoint to the JAL German link main. Okay, set breakpoint and run it. So now single step through it. Okay, now I'm gonna press F10 so you cannot see it, but I actually press X10 to single step through it. Okay, so first we